All right. Here we have, this is just an extension, and there's a packet for homework, and I say it on the back that the numbers we're doing right now as our examples are already 2, 8, 18, and 20 from the packet. So when it comes time to do your packet, we will have already done 2, 8, 18, and 20. Okay? No, you'll just do the rest. Okay? I mean, in general, this is, to me, this feels like just different ways of phrasing things. So it's the same. There's no new concepts today. But it's just different ways of phrasing them, and yes, so a little bit of review as well. Okay. So we have a line that's tangent to a graph, and it's when b is equal to what? So our line is not completed. The first thing I'm going to do is rearrange my line into a format that I like, which is y equals mx plus b. So if I add this y over and subtract the b over, it will be y equals 6x minus b. So if that line is tangent to this curve, how are we going to find that location? If the line equation looks like this, we're looking for a point on the curve that has what? Aiden? You're not going to be able to set them equal to each other because you'd have two unknown variables. If I set 6x minus b equal to 3x squared minus 4, I would not know b or x. The line and the function will touch each other, but specifically at a point of tangency. And when you're at the point of tangency, what about the line and what about the function is the same, Andrew? The slope. So the slope, or the line has a slope of 6. We need to figure out where our derivative is going to equal 6. Follow? Okay? So we need to find our derivative. So, and the alternate form is not helpful here, right? We don't know the location at which we're looking for the derivative. We just know that we want to find a location where the derivative is 6. So we're going to use our traditional form of the limit as x approaches h of f of x plus h minus f of x all over h. And that'll give us f prime of x, and once we know that, we're going to be looking for when that equals 6. So doing some simplifying will leave me with, I'm going to try to do too much at once here, 3x squared plus 6xh plus 3h squared. So I squared out my x plus h, and I distributed my 3 all at once. I do not recommend that the majority of you do that. Square out your x plus h first, then distribute the 3, even though it's going to be more writing for you. Minus 3x squared plus 4 is me distributing the negative sign. Now my 3x squared and negative 3x squared cancel. My minus 4, my plus 4 cancel. The two terms in the denominator both have an h in them, so I can divide by h. So now that h over h is canceled, now I can find the limit. As x approaches, what did I do? Tell me what I did wrong. It's h approaches 0, sorry. Quick fix. H approaches 0. Too many days of the alternate form. Got all twisted and turned around. So if h is approaching 0, then this limit is just 6x. And again, we are looking for when that equals 6. So at what x value will that equal 6? 1. So I know my x coordinate. X equals 1. I need to find my b. But before, if I know x is 1, I need to know what y is before I'm going to be able to find my b. How do I find my y that pairs with 1? Andrew? Right, because this is my point of tangency. So 1 whatever has to work for the line, and it has to work with the function. Well, I don't really know the whole linear equation yet, so finding my y-coordinate from that is not really possible. I'll find f of 1 over here, times 1 minus 4 is negative 1. And now that I know the point of tangency, I can plug it into my line. Negative 1 equals 6 times 1 minus b. Subtract 6, and negative 7 equals negative b. b equals 7. So there's a lot of conceptual understanding necessary to be able to do that. You need to understand how the slope of the line has to be equal to the slope of the function. That requires your derivative. There's a whole chain of events there. So no new concept really, just kind of putting it all together is what I would call this packet that you're going to see. All right, so for what value of x in the interval from negative 1 to 3 does the instantaneous rate of change? Now, instantaneous rate of change means derivative or slope. So does the function have a slope equal to the average rate of change in that interval? Okay, so here's the general concept here. If you have a function that starts here and ends here, okay, the average rate of change is this line right here, start to finish, agreed? There's going to be moments along the curve where the slope is steeper than that and where the slope is less than that, right? This is average because it truly is an average. So every location along the way has an instantaneous slope, and if you averaged all those instantaneous slopes together, you would get the average slope. So sometimes it's going to be greater than that, sometimes it's going to be less than that. But because it's continuous, what we know is there has to be at least one location where the instantaneous rate of change is exactly the same as the average rate of change. And if this kind of elevation of your line is the indicator of the average rate of change, you really can just slide that visually, mentally, slide that until it becomes a point of tangency. So like maybe here, somewhere here, there's a moment where the instantaneous rate of change is equal to the average rate of change. Maybe again over here. Here's another location where the instantaneous rate of change is equal to the average rate of change. Okay, so visually, conceptually, that's what's happening. That's what we're doing here. Okay? We don't care what that function looks like. Essentially what we want to do is we want to find the average rate of change, which we should be able to do. Because you can find the endpoint at negative 1, and you can find the endpoint at 3, and you can find the slope between them. So if I plug in a negative 1, what's my function coordinate? Joey? Try again. Negative 1 squared minus 4 times negative 1. 5. Good. If you plug in 3, you're going to get 3 squared is 9. 9 minus 12 is negative 3. So my average rate of change on this interval is y2 minus y1 over x2 minus x1, negative 8 over 4, negative 2. So clearly my picture is no good because my average rate of change is positive. So your average rate of change is slope, or average rate of change is negative 2. So we want to find out when our instantaneous rate of change equals negative 2 as well. And our instantaneous rate of change comes from the derivative. So we're going to find the derivative of this. and we're going to set it equal to -2 and figure out where this occurs. So f prime of x is our limit as h approaches 0, f of x plus h minus f of x all over h. And I'll be looking for where does that equal -2 once I boil this down. So we have x squared plus 2xh plus h squared minus 4x minus 4h minus x squared plus 4x. After all my distribution, x squared minus x squared gone, -4x positive 4x gone. Every one of those three terms left has an h. So I'm going to divide it out, and I'll be left with 2x plus h minus 4. And now I can let h approach 0, and I get 2x minus 4 as my derivative. And again, I'm looking for when my instantaneous slope equals -2. And where is it? Solve for x, add 4. You get 2x equals 2. So where is it? 1 again. This one just said for what value of x. It didn't say at what point. If it said at what point, I would need to plug the 1 back in to find the y coordinate. If it wanted the complete point, it just said x value. Okie doke? Okay. Okay. Here we have a table, and this table is giving us points. So 0.96 has a 0.671 y coordinate, 0.98, 1, 1.02, 1.04. This wants the derivative, or the slope, at 1. So if you want the slope at 1, what's the best we can do here? So, how so? What do you mean? So, like, what kind of calculation would you do? So what he just did is he's finding the slope between those 2 points. Yes? And that's going to give us, we need a calculator. 0.742 minus 0.671, 0.071 over 0.08, 0.8875. So truthfully, because that was the start of the interval and the end of the interval, you did find the average rate of change for sure, which might be the same as the instantaneous rate of change at 1, but not always. So who's got an idea to get maybe more accurate? I'm trying to think of a visual that would kind of show you why Andrew's method might give you the ballpark, but wouldn't necessarily give you the... Let me hold on one second. Let me just kind of illustrate. So if this is your 0.96 and this is your 1.04, whatever, he just calculated the average rate of change, right? Which would be like that. But if I did like this, is that average rate of change a good estimate for what the instantaneous rate of change is right there? No, that could be very off. Do you follow? Okay. So what was your second thought? Okay. And that's it? I like this. Well, let me just progressively get better. You like took 2 jumps better. So he found the average rate of change, which if it looked something like this, it doesn't. But if it did, that could be very off, right? A positive average rate of change doesn't mean that instantaneously in between it couldn't be very different. So what the first step of improvement would be to pinch even closer. Find your average rate of change from 0.98 to 1.02. So if you moved in from here to here, your average rate of change might be closer to it would probably be closer. It's also not a guarantee though. So what then he did is he said find the slope between 0.98 and 1, which I think is a good idea because that is your slope leading into 1, as close as we can get given the points we were told. But also look at your slope coming out of 1 and kind of come somewhere in between those. Does that make sense? So 0.707 minus 0.689 over 1 minus 0.98. You want to get as close as you can, and we're going to come from the left and come from the right. So this is our f prime at 1 when we come from the left, technically, or at least the best we can do. And then we want to do f prime of 1 coming from the right. So 0.725 minus 0.707 over 1.02 minus 1. 0.018 over 0.02 is also 0.9. Oops, from the right. So because, and if those were off, I would probably just want to land somewhere in the middle. Does that make sense? All right, so that's the idea behind that. And then just getting past even the point where you realize these are points on the function, and this is wanting the derivative or the slope of this at 1. And the slope is constantly changing, right? Did we increase by 0.18? Oh, no. Right. It does increase pretty steadily by 0.18, 0.18, 0.18, but then the last one throws it off. I wish it didn't do that, but oh well. It's just what the problem I stole this from did. It would be nicer if it was constantly changing. But that's how you would use a table of values to the best of your ability to find your best guesstimate for what the slope is at 1. Okie doke. All right, on the back. Okay, we are given f of negative 2 equals 1. I don't know if this is going to be worthwhile, but that's a point on my original function. So at negative 2, we're at 1. The slope at negative 2 is a positive 5. So wherever the function is going through this point that they gave us, it has to be with a slope of 5. So that's pretty steep. Agreed? I have no idea what it's doing much beyond that or prior to that, but instantaneously as it goes through that point, negative 2, 1, it is with a slope of 5. So it's a steep positive. If the tangent line to the graph of function f at x equals negative 2 is used to approximate the value of the 0 of function f, then that approximation would be. So if this is increasing with a slope of 5 through that point, like, again, it could do any sort of crazy thing beyond and any sort of crazy thing prior. But because negative 2, 1 is not far off the x-axis, it doesn't have much time to turn around and miss the x-axis. So what they're saying is, if we're going to use the tangent line here to estimate the 0 and where our graph is going to cross the x-axis, where would that 0 be located? Where would that root be located? So we essentially need to write an equation of the tangent line. So the line has to go through point negative 2, 1, and it has to have a slope of 5. And once we write the equation of that line, we're just going to find the x-intercept of that line. We're going to find out where that line crosses the x-axis, and that's going to be our best approximation, given that we have such limited information about our polynomial function. That's going to be our best estimation as to where the x-intercept of the curve is going to be. Any questions on that logic? So write the equation of the tangent line. I'm going to turn it into slope intercept because I like that better. And then I'm going to find the x-intercept. How do you find an x-intercept? Right. So negative 2.2, which makes sense because it should be a little bit further left than that point at negative 2, 1. Again, it's just an estimation. We don't know enough about the function to know exactly where that's going to happen, but because that point of tangency is so close to the x-axis, it's worth giving us an estimate. But truthfully, this could really turn around right here. It would have to be a very quick turnaround given that that slope of 5 is pretty steep. It doesn't have much time to progressively turn around, but it could. But again, best estimate. So that answer would be negative 2.2. Okay, so let me find your packet and I'll hand that out. And we've already